Welcome to this video on the wave function and quantum mechanics. As the title suggests, in this video we're going to be taking a look at the famous or perhaps infamous wave function and how it's used as a tool to make predictions and classifications in the study of quantum mechanics. I'm also going to be using images and examples again from the openstacks.org University Physics Volume 3 text, and I have a link in the description below so you can check that out for more practice and other awesome background and examples. So let's get started. Over here I have two images of two different mechanisms that we've looked at before in this quantum, nuclear, and atomic physics unit, and they are the first one being nuclear fission and then electron movement within the energy shells of a Bohr model atom. Now, why I have both of these up here is because we know the resulting mechanisms that occur in each case. However, we are unable to predict which particular atoms will undergo nuclear fission, and we're also unable to predict when and if a particular atom will undergo nuclear fission. Similarly, we are not able to predict if an electron that's, say, at energy level 5 will fall all the way straight back down to level 1, or if it will stop at 4, 3, then 2, and go to 1 on its way down. So there are certain things that we do know, but we are unable to pinpoint to the exactitude that we were able to do when we were studying earlier classical mechanics and classical physics. And so what we're going to look at in this video is that foundational idea that we're unable to make predictions on where and how, and sometimes even when something's going to occur, but we can do it as a holistic or probabilistic approach. So we're going to go back to mechanics for a minute, just old school classical mechanics. And if you think about classical mechanics, we know that it's the science of describing motion. And classical mechanics started with some functions. We could tell an object's position as a function of its time, in other words, where something is at a given time. So therefore we could make predictions on how far it would have moved in a given amount of time, or where it had been in the past. We can also do this with velocity, acceleration, and we could even do the velocity of a particle as a function of its position. And all of these things here, we're describing a macroscopic object. And a macroscopic object as almost just a center of mass, or a simple box. It was an oversimplified analysis of objects, but it worked. You could make predictions on where something was going to land or how far it moved based on different parameters that each of these functions outlined, and they actually worked. They did produce results and predictions. The problem was that when scientists were first looking at these ideas of very small amounts of movement or very fast movement of very small objects or subatomic particles, in other words, when we first started to encounter the quantum world, where things only happened in weird bursts or in only certain stages or discrete amounts or packets of energy that we've seen before, all of a sudden these things didn't work anymore. We couldn't predict the electron movement. So these are not a good predictor of electron motion. They're not a good predictor of where the neutron's gonna strike. They're not a very good predictor of will the electron fall from 5 straight down to 1 or bypass certain levels or stop at certain levels. And so what needed to happen was we needed to come up with a new system that could explain the motion of these subatomic particles. And this is known as quantum mechanics. So we're going to take a look at some of the assumptions that we're going to make here, and then look at the tool, the wave function, that allows this to happen. Now keep in mind, we're doing the very basics of this introduction to the wave function. There's so much more to do, and so I really encourage you, if this is something that's interesting to you, to go to the openstacks.org Physics Text Volume 3 and check it out, because there's some really neat stuff in there. Well, one of the things that seems the most obvious is that systems are made of particles. And we've already talked about actually all of these things when we studied thermodynamics. And if you think back to thermodynamics, one of the things that we had to do in that area of study was look at something that was called statistical mechanics. And what we were looking at with statistical mechanics was the idea that systems are made of particles. So not everything is just macroscopic and behaves as a whole big box. Not all particles behave the same way that make up the system. And so the individual particles are not necessarily predictable. In fact, they aren't predictable. But we can use statistical models to describe the probability of various outcomes. In other words, we can make predictions about what's going to happen from a probabilistic standpoint. We're also acknowledging, however, that other things or other outcomes are possible. So I'm going to draw your attention back to a graph that we looked at before, known as a Maxwell-Boltzmann distribution. And if you remember, Boltzmann was attributed with defining entropy from the statistical mechanics concept, and it was really ingenious. And it's sad that he didn't live to be much older, because he probably would have had a really great impact in quantum mechanics as well. So if I draw two different curves on this graph, I have this first curve, and then maybe I have a wider curve like this. If you think back, the wider curve had a lower peak, and the graph was a representation of the average speed of particles within a system of gas, and this was the probability density of particles within the gas. So what we were saying here is at a particular temperature, let's call this 3000 Kelvin, this purple curve here, it displayed the spread of different possible microstates that could contribute to a given macrostate. So the macrostate was me labeling the gas as a temperature of 3000 Kelvin, which was really a measure of the average kinetic energy of the particles. Not all particles were moving at the same speed, but the ones that were right around the middle to the right, the root mean squared, and that was the most probable density of particles at that speed. Now, as things shifted to cooler temperatures, let's say this one's at 1800 Kelvin, we saw the peak rise and the spread decrease. And the reason that we had to see this happen was the probability of all the particles in the system has to always be 100%, because all the particles are moving in some way, shape, or form, but there's less variation in the particles at the lower temperature than there were at the higher temperature. Now, we're not talking exactly about the same thing in this example, but we are giving a very similar take to predicting where is an electron going to be at a given time. But we're going to spin this just a little bit, because this is a little bit misleading sometimes, because we know that electrons can exist in multiple different energy states. So instead, what we're going to say is we're going to use this symbol called psi, which is known as the wave function of an electron, and it's going to be able to tell us a couple different things. One of the things is the probability density of finding an electron at a particular place, and also the probability density of finding an electron at a particular time at a particular place. And so again, it's not picking a specific electron and telling us exactly what's going to happen. What it's going to do is say the probability density of finding an electron at a specific place is going to be best explained through a probability density graph. So I'm going to give you an example of one first, and then we will look at a more specific one to electrons. So let's say that I have a PVC pipe, and the PVC pipe has a length of L, and I'm going to label it along the PVC pipe from 0 all the way to L. And I want to construct a graph that shows where a ball placed on the inside of the PVC pipe can be. What's the probability of it being anywhere along this length L? Well, if I make this my probability axis over here, my wave function axis, and this my position axis, what I could say is that the probability of the ball being at any specific location, x, along this PVC pipe, we know a couple things for sure. At 0 over here, and beyond 0, there's going to be no probability of finding the ball in the pipe because it won't be in the pipe. And at length L, let's say that occurs over here, after that, we'll see 0 probability of it being anywhere else. But at any other time, there's an equal probability of finding it at any other place. And so we might draw something that looks like this and not something that looks like a curve, because it's not possible for it to be on the outsides, and it's not more probable for it to be in one place than another. So what's the probability of finding it, say, at somewhere to the left of center? Somewhere over some position, let's call it x instead of L, to the left of L over 2 between 0. Well, if you think about it, if we did up to L over 2 over here, we could find that probability, and it's easy to see, hopefully, that it would be 50% probability that it would be found somewhere on the left-hand side, and 50% probability of somewhere on the right-hand side. And so what we're trying to do here is, rather than describe exactly the kind of motion that the ball is going to experience, we want to be able to explain or show the probability of it being in certain places at a given position. So how certain can we say we are that the electron, or an electron, is located at position X? Now, it turns out that when we're dealing with a particle like this, it's a little bit more simplified than what's going to happen when we're dealing with something that's subatomic, or we're dealing with something that's acting as a wave. So here, this particle is acting as a particle. So it really doesn't make sense for me to use a wave function necessarily to explain its position, its possible position. Instead, what I could do here is, describe a kind of movement and then tell you where the ball could exist. So let's move away from this idea for a second and take a look at what exactly it's going to mean now to do the same kind of probability strategy that we just drew for the ball in the tube, but for an electron, or something that's behaving like a wave. So over here, there's a series of pictures. This first one you can see very clearly is an interference pattern, or a diffraction pattern. And this interference or diffraction pattern is very, very often the thing that we use to help describe what a wave does. It's a wave behavior. And a wave behavior, of course, is something that a particle doesn't exhibit, or we don't observe it exhibiting, at least on the macroscopic scale. So over here we have a series of images that are kind of a time delay. So we have a snapshot over time over what's happening here. And I have a low intensity light that's monochromatic, and it's shining through a double slit. And as photons, which we know behave as waves, but sometimes also behave as particles, this wave-particle duality, we see that the probability of photons show up in this cool intensity pattern. The places of high probability show with high intensity, and the places with low probability show with the dark bands, or the low intensity places. And we saw from the de Broglie wavelength, which, if you remember, could be calculated from the momentum of a particle and its mass, we saw that even particles that are moving very, very fast and have very small masses can have wavelengths that will allow those particles to behave as if they were waves. So instead of photons, we're looking at electrons now. And again, we could describe the electrons as having wave-like properties, and also having particle-like properties, just like the photons. So we said photons can interfere and diffract, and electrons can do the same thing. And so if we're trying to describe where electrons are going to be, we can't only describe them in terms of their most likely position, as in the ball and the tube, because the electrons can also interfere with one another. And that interference and that diffraction and all the other things that the electrons can do, behaving as waves and not only as particles, is going to have us use the wave function. So over here I have 6 graphs, and I'm going to label them A prime, B prime, and C prime, because graph A and A prime are actually of the same motion, but A prime is the squared wave function, whereas graph A is not squared. And the reason that we square it is to get rid of these negative probabilities over here, and you can see that it causes the entire graph to become positive. So when we look at this graph, what we're basically saying is that we're graphing the wave function, the probability density. Now this takes into account many different aspects of the particle's motion. Maybe other forces acting on it, some complex numbers. It could be a whole lot of things, and that's not the point of this video specifically. More, we want to think about this being a probability density of finding an electron at a particular position. And you can see that the peak is highest over here. In this case, in this graph B prime, we see that there's 2 peaks. There's 2 places where it's more likely to find the electron at some specific position X, and there's certain places where it's not really probable or likely at all. Again, here we see this tiny little hump, a zero space, and then a very distinct place of where the electron might be. So if we had a higher peak, if I was to superimpose another graph on this one, and I'm going to call this purple graph D prime, I would say that D prime has a greater likelihood of knowing where the electron is than A prime's graph did, because it has a higher peak. And if I was using the same number of molecules, I should probably make this peak a lot slimmer to keep the probability at 100% in terms of the total. So when we look at electrons as being in certain energy positions, if I scroll back up to this first part that we looked at before, we can see that there might be more probable states or energy levels at n equals 1 to find an electron, and other probable states at say n equals 2, n equals 3, and so on. And these happen to be integer multiples of the wavelengths of the electrons. If the wavelengths of the electrons overlap with each other in phase and we have constructive interference, that's a place where we're going to be more likely to find an electron. Whereas wherever they occur at specific energies or specific photon absorptions at places in between these levels, those are going to be non-whole number integers, and the electron de Broglie wavelength is not going to overlap, and so what's going to end up happening is it's not going to be a very likely place for HEP to be found. And we can even get to the point where it's completely unlikely to be found in, say, these dark regions where the wave actually completely destructively interferes and we're not able to find it. So when you look at the wave function, although if you were having to do a lot of the mathematics, it can be very complicated, and sometimes the only way to solve is to use a computer, but we could look at a graph or compare 2 different graphs and say what we think or where the electron is most likely found, or perhaps in which graph would the electron be more probable, or in which sample would the electron, knowing the electron's position, be more probable. So the big takeaways from this idea about the wave function is that it's a way for us to predict, just like the classical mechanics concepts of predicting the speed and the position and all these different things. It's a way to predict for a system or how electrons work in general. This is a statistical model that assumes that systems are made up of lots of particles, and not all the particles are behaving in the same way. And therefore, no individual particle is predictable, but as a whole, we can see how they might be predictable by their nature. This is true of all other subatomic particles as well, and can be studied in a lot of different cases. One of the biggest ideas in physics that Einstein set out to achieve was to try to unify relativity and quantum mechanics. And it is yet to be completely unified because some of the ideas just don't seem to gel with one another. But more on that another time.